Hello everybody, this is Mr. Hudson. I'm just going to go through some notes here for you covering section 4.2. What you should do is take some notes here, and then in our next class you will actually be working on an assignment based on these notes. This section covers what's called the natural exponential function. Again, this is section 4.2. I'm going to start off with, there's a lot of things in the sections that goes back to some things that you've done in the past. This first is a simple interest formula, and you should probably write this down. The simple interest formula is I equals PRT, where I represents interest, P represents the principal amount, not Mr. Tobin, it's an amount of money, at a rate which is R and is expressed as a decimal per year for T years. So again, I represents interest, P represents principal amount, R represents the rate written as a decimal, and T represents time in the number of years. I'm going to write that formula again here, I equals PRT, and here we have that Bill deposits $2,500 into a bank for 10 years at a simple interest rate of 5%. So as we look at that formula, I would have I, the interest, for the interest that he would receive, equals the amount of money, which is $2,500, times the rate, which is 0.05, times time, which is 10. So I'm going to go ahead and plug that into our calculator here. That would give me $2,500 times 0.05 times 10, and this is the amount of interest that he would receive, and that interest would be $1,250. $1,250. And again, that is the amount of interest. That's not the total amount that would be there, that's the total amount of interest. Now this says how much money will he receive at the end of 10 years, and that's asking for a total amount. So if you take the $2,500, his original amount, add that to the interest that he has received, that would give us $3,750. And that would be the total amount of money that he would have after 10 years. You can buy quite a few calculators with that. Now, if you were to deposit some money into a bank, you actually would, usually you see it compounded. What we do is we take a certain amount of money, and maybe after 6 months you take a certain interest rate of that, and then after another 6 months you take interest upon that interest that you have received. In that particular case, what we have is this formula, and you may recall this formula from Algebra 2. A represents the amount, the total amount after so many years. P represents the principal amount, the original amount that is there. R, again as a decimal, is your interest rate. N is the number of compoundings per year. For example, if it is compounded monthly, if that amount is compounded monthly, then N would represent 12. If it was compounded semi-annually, then it would have been twice per year. If it was monthly, it was 12, semi-annually 2. If it's quarterly, a lot of times you would see quarterly, that would be 4 times per year, and so on. And obviously T represents the number of years. So again, I'm going to write that formula here. So I have A equals P times 1 plus R over N taken to the NT power. Here we say the bill deposit is the same as before, $2,500. So we've got $2,500 times 1 plus the rate, which is 0.05, over N. Now this is compounded monthly, so N is 12. And that is going to be taken to the 12 times 10th power. Now you have to be careful when you are plugging this in to your calculator. What we're going to do is we're going to take $2,500 times 1 plus 0.05 divided by 12. Okay, I'm going to close that out. I'm going to take that. Now, a lot of times you could actually just go ahead and multiply this out, so we know that's going to be 120. If we're going to let the calculator do this for us, then we're going to need to make sure we put that 12 times 10 in parentheses. So put the entire exponent in parentheses, otherwise you will not get an accurate answer. And our value will be $4,117.52. So we get $4,117.52. Now the question here is, how much interest will he receive? Well, for the amount of interest, let's take that total amount that he had and subtract the $2,500, giving us $1,617.52. That's how much interest Bill would have received. Pretty good. Now, if we look at this compound interest formula, as I said earlier, you could go monthly, you could go even daily, and so on. But as this denominator gets larger and larger and larger, we look at this 1 plus r over n to the nt power. It's kind of interesting. If you plug in maybe 10 for n, and then plug in 100 for n, and then plug in 1,000, and then plug in 10,000, and keep going and going and going, that number approaches what we call the letter E. And E, it actually stands for a guy's name. His name is Euler. But E actually represents the numerical value of approximately 2.718. If you look on your calculator right here with that natural log button, if you hit second in natural log, that e to the x, that E represents, in fact, if I type in here E to the first power, that is approximately 2.718. So when you see that letter E, that's what that is referring to. There's actually a formula. If we compound an amount continuously, not just by the day or by the hour or by the minute, but literally continuously, this is a formula that allows us to find that. And I like to refer to it as the PERT formula. Kind of like the shampoo, you have P-E to the RT power. A represents the amount after so many years. P represents the principal amount. R is still the rate. T is the time. This is only going to be used when we are compounding continuously. So here, notice how it says we are compounding that same amount continuously. We would take 2,500 times e to the 0.05 times 10th power. That would give us our amount. So if I plug that in, I'm going to go 2,500 e to the, now the parentheses are there for us already, so I can go ahead and type in 0.05 times 10, or I could just put in 0.5, and that would be $4,121.80. $4,121.80. And notice how the more we compound something, the more money we're making. So you always want to, if you have a choice in the matter, you always want to compound as often as possible. So this has an interest of $1,621.80. So when we talked about that e, the e to the x, that is what's known as a natural exponential function. Because it goes along, on the calculator, notice how that went with the natural log. Well, e to the x and natural log kind of go hand in hand, because a natural log is one with the base of e. So the function e to the x is what's called a natural exponential function. Now in our last section we talked about graphs of some of these exponential functions. This is the graph of f of x equals e to the x. We of course have our y-intercept there at 1, and then since that that exponent is positive, this is increasing, so this is what we call exponential growth. And it's growing at an exponential rate. How we're going to use that is, again, similar to what we did in the last section, and that is to use some transformations to sketch some of the graphs of these exponential functions. Now what we have is f of x equals e to the x minus 2 power minus 5. Well, some of these transformations that we've talked about before, if you have some number with the x, that is going to be a horizontal shift, and if there's a number that we are adding or subtracting to the entire function, that is a vertical shift. So what we'll do is, I like to start at this y-intercept, where that's the 0.01 of the original function of f of x equals e to the x power. And we're going to take that graph, and I'm going to move that 2 units to the right. So I'm going to go right 2, and then I'm going to move it down 5 units. 1, 2, 3, 4, 5. So I'll go to the right 2 and down 5 units. Okay, so there, it's almost like I'm looking at this graph and saying, all right, let's move this to the right 2 and down 5. Also, this has a horizontal asymptote at y equals 0. Since we're moving down 5 units, then we're going to go down 1, 2, 3, 4, 5 units here and have a dotted line there. I'll try to be as straight as I can. That will be our horizontal asymptote. So our graph is going to look something like this. I have to be careful to make sure that does not touch the horizontal asymptote. So that's how we can use transformations to shift these exponential functions. Now a model for either exponential function or, growth or decay is this a of t equals a sub 0 e to the kt power, where a of t is the total amount, is the total amount after so many years. A sub 0 is the original amount, or the initial amount. K is the relative rate of growth. A lot of times you even see this as an R. We're going to use K because that would be a constant number. Now it's going to be a growth if that number is greater than 0, or decay if that exponent is less than 0. And then T would represent time. So let me write this again. We had a of t equals a sub 0 e to the kt power. What we've got here is it says assume that there were 1 million bacteria in a dish. Assume that the amount of bacteria increases by 10% every hour. Estimate the number of bacteria in the dish after 20 hours. So we're going to find a of, it says after 20 hours, so a of 20. Where a sub 0 is 1 million. E is what it is, E. It is increasing by 10%, so that's 0.10 times 20, that's our t value. So I can plug this in here. I'll go 1 million E to the 0.1, or 0.10, I guess I could write, times 20. And that would give me that number. And I'll let you write that down. That is 738,905,609.9. And that would be the amount of bacteria after 20 hours. Now here, if we're to go after 3 days, well, let's not forget that this was 10% every hour. So what we're going to have to do is figure out how many hours are there in 3 days. Well, take your 24 hours in a day, multiply that by 3, and you'll get 72 hours. So what we'll do here is we'll find a of 72. We take 1 million and multiply that by e to the 0.10 times 72. And I can use the same formula I just did, except I'm going to change this 20 to a 72. And as you can imagine, you get a pretty big number here. So big, in fact, that your calculator is giving that in scientific notation. So this, we could look at this as 1.34 times 10 to the 11th power. And that one I'll write down. 1.34 times 10 to the 11th power. And again, that's the number of bacteria after 20 hours. Okay? So you're going to come to class tomorrow and work on this assignment. Don't worry about doing it now, but this is what you'll be doing in class tomorrow. I'll give you this assignment again tomorrow. Hope you enjoyed this as much as I did, if not more. Enjoy your night.